What if you could take a system's greatest weakness, the very thing that's always threatening to tear it apart, and somehow flip it, turning it into its most powerful tool? Well, in the absolutely wild world of quantum mechanics, that's not just a thought experiment anymore. It's really happening, and it might just change everything.
All right, so here's how we're going to break this down. First, we'll tackle the central puzzle of entanglement. Then we'll get into this wild new idea of actually using quantum noise. We'll walk through the experiment itself, see if the numbers hold up, and finally, look at what this really means for the future.
So, let's start with the fundamental challenge. You see, scientists are working with one of the most powerful resources we know of in the entire universe. But it's also unbelievably delicate.
And that really is the million-dollar question, isn't it? Seriously, just imagine trying to build an intricate house of cards, but you have to do it in the middle of a hurricane. That's pretty much the daily battle for quantum engineers.
This is the house of cards they're trying to build. Entanglement, right? That spooky action at a distance that connects particles no matter how much space is between them. It is the absolute bedrock, the foundation for all the quantum tech we dream about. And this is the hurricane. The dissipative environment is just a fancy way of saying, well, reality. Everything, a tiny vibration, a slight change in temperature, a stray magnetic field, any little whisper from the outside world can come in and just obliterate that fragile quantum connection. It's always been seen as the enemy.
So how in the world do you solve a problem like that? Well, you start by completely flipping the script. Instead of fighting the hurricane, what if you could actually learn to command the wind?
Yeah, this really shows you the massive shift in thinking. For decades, the entire strategy was about building a perfect fortress, total isolation. But this new approach is it's so radical. It says, forget the fortress. Let's actually open the doors and intentionally let in some controlled noise and use that noise as a sculpting tool. This quote just nails it, doesn't it? It's a total paradigm shift. Stop fighting your environment and instead figure out how to make the environment an active partner in what you're trying to create. It's brilliant.
And this is what they call it, dissipative engineering. Now, the key word here is controlled. This is not about letting chaos run wild. It's about using a carefully engineered dose of dissipation to gently but persistently push or pump the quantum system right into the exact entangled state you want, and then keep it there.
Okay, so that's the big idea. But how did the researchers actually pull it off? I mean, how do you use lasers and ions to literally sculpt a quantum state out of something that used to be considered just junk noise?
Right, let's look at the toolkit. The system, the thing they wanted to entangle, was the physical jiggling, the vibrational modes of these trapped calcium ions. The dissipative bath, their source of controlled noise, was actually the internal spin state of those very same ions. And the tools they used to link the two? You guessed it. Incredibly precise lasers. And here's the basic recipe. Step 1. A laser connects the ion's vibration to its spin. Step 2. A different laser comes in and resets that spin. Now that reset, that is the key act of controlled dissipation. It's like it's carrying away all the unwanted energy and information. And you just repeat that cycle over and over and over, essentially herding the system step by step closer and closer to your target.
And the end game here is just so clever. This constant pumping process basically makes every other possible quantum state unstable. They all just naturally decay and flow towards one single stable configuration that's immune to the process. They call this the dark state. And it just so happens to be the exact perfect entangled state they were trying to create in the first place.
So that's the elegant theory behind it all. But this is where the rubber meets the road. The big question is, did this quantum sculpting actually work? Let's take a look at the data. Oh, it didn't just work, it worked beautifully and at scale. They successfully used this method to entangle 2 different vibrational modes, then pushed it to 3 modes, and then all the way up to an incredible 5 distinct modes. That's huge because it proves that technique is scalable. And the quality of the entanglement? Just wow. For the 2-mode state, they hit an estimated fidelity of 86%. Now, to put that in perspective, that means the state they actually made was an 86% match to the theoretically perfect one they were shooting for. In this field, that is an absolutely fantastic result. And here's the kicker. It wasn't a fluke. They were hitting these amazing fidelities, around 84 to 86% across the board, whether it was 2 modes, 3, or 5. That tells you the method isn't just clever, it's robust, and it's reliable. Okay, but hold on.
This is the critical question you have to ask in any entanglement experiment, right? It's one thing for the state to look right, but you have to prove mathematically that these different parts are truly deeply linked in that weird, non-classical way.
And here is the proof, plain and simple. They used a standard test, and the rule is pretty easy to follow. You measure a specific parameter, and if that number is less than 2, you have genuine, bona fide entanglement. We'll look at their results. For 2 modes, they got 0.42. For 3, 0.6. For 5, 1.07. All of them are way below that critical threshold of 2. That right there is the smoking gun.
So, what does this all add up to? Why is one successful experiment getting people so excited? Well, it's because this isn't just an experiment. It's a demonstration of a whole new capability.
See, the breakthrough here isn't just about making one cool entangled state. The method is programmable. By just changing the laser instructions, scientists can now cook up a whole menu of different, complex entangled states whenever they want. And because it works with more modes, it's scalable. It's like going from having a single specialized wrench to having a whole programmable toolbox.
And what can you build with a new toolbox like this? Well, how about brand new types of quantum computers? Or advanced simulators for designing new drugs and materials? Or even sensors that can measure things with a precision we've never seen before. And this basic technique could even be adapted to totally different kinds of quantum hardware.
Of course, this didn't just happen overnight. The core theory was actually worked out way back in 1996. It took nearly 2 decades until 2015 for someone to finally make it work, but only for a single mode. And now, we've got this programmable multi-mode powerhouse. It's a huge leap, and it's paving the way for the kind of robust on-demand entanglement that future quantum computers are absolutely going to need.
And that really just leaves you with one final thought, doesn't it? This research took a problem, the biggest problem, and turned it into the solution. It makes you wonder, what other fundamental rules or limits that we all take for granted are just waiting for the right person to come along and look at them from a totally different angle? What other impossibilities are about to become possible?